coming back to our understanding of difference between regression and classification. Now, as we discussed, the purpose is to find out whether it belongs to category X or category O. So let's pretend 1 means category O. And remember, we also use the terminology class instead of a category. Okay? And class or category, if it is class X, will output a 0. In reality, depending on how much training we do, how good of a network we create, okay, the output will not be exactly 0 or 1. For example, let's again imagine this is 0.3x plus 2. So if we feed in, let's say, x1, x2. Okay, suppose I feed in x1 of 2, x2 of, let's say, 2.1. Okay. So if I feed in 2 over here, right? So 2 times 0.3. So exactly on the line, as you can see for x of 2, it has to be 2.6 to be exactly on the line. Okay, but what are we feeding in for x2? 2.1, which means we're feeding in really a point below. So which category does it belong to? X category. So the expected output of, if it is trained properly, will be what? Close to 0. In reality, you may get 0.1. Sometimes you may even get 2.25. As long as it's below 0.5, again, depending on how good of our training and how much data do we have for training. So below 0.5, we may mean class X. Above 0.5, we may mean class O, right? Okay. So coming back to your second part of the assignment was the problem I gave you was not for regression, but for classification. So okay, so basically you were given x1, x2, okay, so you have W1, W2. So how many model parameters you need to determine now? 3, W1, W2, and B, right? So just like before, you'll set up, you need to know the gradient with respect to W1, gradient with respect to W2, gradient with respect to B, right? So can you, let's pick one example. Let's go to W2. What would be the equation? So partial L over partial W2 is what we are interested in. So again, easy way, like I said, is determine the path. The path over here will be to W2 will be this green line over here. Okay, and what were we calling this part? A. S, and this one, A, right? So this will be partial L over partial A. Partial A over partial S, partial S over partial W2. Okay, but how do we know? So this is easy. This will be same as minus Y minus A, right?
This is 1.
This is 1 so far. Okay, so this is the one, right? For this one, write the equation. What's the equation for S? X1 times W1 plus X2 times W2 plus 1 times B. So what will be partial S over partial W2? X2, right? Because this is the variable, so everything else is a constant, so the derivative is 0. So this will be simply X2. And so this way now you can do partial. So in the assignment, what I will expect you to do is show me the derivatives. Okay. Then write the code to train it. I already gave you the training data. What is the x1? What is the x2? The expected output, because we are assuming y equal to 0.3 x plus 2. The expected output, I think I also gave you in a table probably, whether it's a 1 or a 0.
Yeah.
Okay, then some of you email me, oh, when the expected output is 1, you're getting 0.75. When the expected output is 0, you're getting 0.25. That's okay, because remember, we only trained it for like 6 training data. Okay, as you will discover as we go along, I'll give you an example. I have some code that I'm working with some PhD students related to face recognition. And for us to be able to do really good face recognition, we needed 3 million images. Okay, so this is our training data. And still, sometimes it doesn't do as good of a job. So, as we go along, we'll see the importance of data, what are the issues, training issues, and so on. Okay, but for right now, with the 6 data, it won't be exactly what we want, but it will be close to what we want. Okay. Yes.
You can create the data using the equation. I'm using like in 1000.
Yeah, you could create your own data. But pretending we only were given 6 data, then that would be the expectation. Okay, so now that we have an idea about a single neuron network, okay. So as we discussed in the last lecture, okay, when we take a look at how the single neuron network behaves, okay, what is this an equation of? It's a linear, right? Whether it's in 2 dimensions, it will be line, and 3 dimensions, as we discussed, it will be a plane, but it will always be a straight line. There won't be any curve involved to it, okay? So as I will show you later, sometimes our decision boundaries are non-linear. Okay, so the data may be separated like something like this, right? So this is where we need more than one neuron, okay? If you already know in advance, oh, the data is linearly separable, there's no need to create a complex neural network. A single neuron will do the job, okay? There's a variation of it called logistic regression. Once I put the logistic function over here, then I can clarify it. But for the time being, logistic regression is a single neuron system. So what is it capable of? What kind of decision boundary it's capable of learning? Linear. Okay, so that's all you have to know for right now. So now let's try to make things more involved so that we can create nonlinear decision boundaries. Okay, so now let's go to, let's say, a 2-neuron system. Or let me make it even so that we can save some time over here. Let's create 3 neurons. So our system will be something like this. Okay, and let's again suppose we are doing the classification. So x1, x2. Okay, so most of the networks that we'll create in the beginning will be called dense networks. In a dense network, all inputs go to all neurons, and if there's another layer involved, the inputs will go to every neuron in the next layer. Okay, so both x1 and x2 not only will go to the top neuron, but they will also go to the bottom neuron, the same input. Okay, every neuron has its own bias. So here will be a bias. Okay, depending upon how we label these, okay, we can easily come up with the training equations. Okay, and by the way, because the lines that feed to the top neurons will have their own weights, W1, W2. And same way, I could call this W3, W4, W5, W6. I mean, that would be one way of doing it. But we need to develop a little bit of a consistent terminology so that if we go to multiple neurons, multiple layers involved, we can easily analyze them and come up with the training. Okay, so our terminology will be something like this. W, input, sorry, output number, comma, input number. And then further, what we'll do is, at the top, this will be the layer number. Okay, so in other words, okay, think of this as output 1, output 2. So we'll go 1, 2, if there was one more, 3, 4, and 5, right? So, okay, so output 1, right? And it's coming from the first input. So output number, input number. Okay, why don't we do it input number, output number? Later on, I'll show you the benefit of this technique, because once we convert to matrix form, this will help us easily convert it to matrix form. But so that's the motivation, we put the output number first. Okay, so now this is output 1, right? So what will be the
W1,
1? And what's the input number? 2. Let's go to this one. This is output 2.
1.
So this will be W2, and it's coming from input 1, right? And same with W22. This is layer 1, so I'll put a superscript over here, 1, 1, 1. Okay, let me call this S1. Let me call it A1, because this is layer 1, S2, and A2, right? Okay, so same way over here, there's only one output over here, so let me call it W11 of 2, and W12 of 2. Okay, this will be S2 and A2. Okay, now we can put a loss function over here. Okay, so this one will be the loss, and this one will be the expected output.
Yes. Second neuron, is it S2 and A2?
This one? Oh, this is the first layer. Yeah, let me put 1 over here, 1 over here. Thank you for pointing that out. So this will be S2 of 1, A2. Yes, so thank you. Okay, so how many model parameters do we have now? Our model parameters are now actually,
6.
okay, let's call this B1 of 1, B2 of 1, and B1 of 2. Okay, so we have 9 model parameters now that we need to optimize. Okay, what are those? W11 of 1, W12 of 1, W21 of 1, W22 of 1, B1 of 1, B2 of 1. So that's the first layer, right? And in the second layer, we have W11 of 2, W12 of 2, and B1 of 2. Okay, so those are the 9 gradients we have to determine. So then based on the training data, we can train it and have it learn whatever function we want it to learn, right? Okay, so let's remember the same path rule so that we can divide the derivatives into a chain of derivatives. That will make it a lot easier. So let's first start with the easy part. Okay, let's go up to this point and figure out what will be partial loss over partial W11 of 2. Okay, what's the path involved over here? Partial
Partial
L,
A1 of 2,
A of 2.
then partial A of 2.
Or let me call it S1, A1. You're right. Let's make it this one, right?
Partial
Then
A1 of 2.
partial A1 of 2 over
Partial S1 of 2.
S1 of 2 times
Partial S1 of 2.
partial S1 over 2 over
Partial W1 of 2.
W1. Okay, this is easy, right?
Y1 of
Minus y minus.
A1 of 2.
Okay, what's this one?
1.
1. Okay, so to determine this, again, write the expression for S1 of 2. What's the expression for S1 of 2?
X1.
It will be, no, there's no, the input is A1 of 1 times W11 of 2, right? Because this gets multiplied over
Yes.
here, plus A2 of 1, that's the input feeding to this one,
W1 of 2.
W2
1, 2 of
plus 1
minus.
B1 of 2. Okay, so what will be now partial S1
A1 of 1.
over W1 and 2? You can see you just A1 of 1, right? So this will be A1 of 1. Okay, very similarly, without me going into all the details, hopefully you'll be able to tell me what this will be. So now I need this gradient.
Minus 1 minus A1 of
So will this stay the same? Or-
Yes.
See, now the path is like, take a look, the path is over here. Right? So this stays the same, this stays the same. Only part changes is the derivative of S1 of 2 with respect to W1 2. So it will still be
1 plus 1 minus A1 into 1.
times.
2 of 1.
Now go to this one, S1 of 2 will be doing derivative with respect to W1 of 2, right? So it will be,
A2 of 1.
okay, so we are done. Now let's go a little bit, let me pick one of these and then the rest you'll be able to see it yourself. So let's go to, for example, this green path that I showed you. Okay, how would you determine this? So this is, so now we want to determine partial loss over W1 2 of 1, right? So again, this will be, let me first write all the derivatives over here. Partial L over partial A1 of 2,
Partial
A1 of 2 over
S1
S1 of 2 times
S1 of 2 of 1.
partial, A1 of 2 over S1 over 2, S1 of 2 over
A1
partial A1 of 1,
into
partial A1 of 1 over, and then partial S1 of 1,
W1 2 of 1.
W1 2.
No.
No, we are just determining the gradient. Okay. Okay, so now it's easy. What's partial L over A1 of 2?
Minus y minus A1 of 2 into 1
Into 1, this is 1.
into A2 of 1.
S1 over partial S1, okay, with respect to A1.
So are we
Oh,
okay
yeah.
with
That's S1 of 2.
Wait, which one am I doing? I'm doing S1 with respect to, right? So let's write the equation for S1 before we do the derivative. So what's the equation for S1?
x1 times w1 of 1
1
plus x2 times w1 of 1 plus 1 times v1 of 1.
Okay, so now we need to take this.
That's
This
S1
right
of 4.
block. This is, I made a mistake. S1 over 2 over A1 over 1, right? So I need the equation
S1
for
of 2.
S1 of 2, which is already here. So with respect to A1 of 1, so this will be
w1
W1, 1, 2. Okay, now let's go to this one. A1 of 1 over S1, which is the activation
One.
function, which is 1, correct? And lastly, S1 over
X1.
Now we take a look at this equation. Okay, with respect to W1, 2,
x2
X2. Okay, so same way, like I said, now you can go figure out partial with respect to W1 or W21 or W22. Once you have the gradients, like I said, you'll do a forward pass, store all the outputs, then you'll do a backward pass based on the error, you'll compute the gradients, and then each one of these you will adjust. So for example, W1, 2 of 1 will become W1, 2 of 1, or whatever was the original value, minus learning rate
into the gradient.
times the gradient W1, 2 of 1. And same thing for the other 9 values, right? Okay.
Learning rate is arbitrary.
Learning rate, we'll look into it more detailed. By the way, before I forget, next week I'm not here, so we'll have an extra class this Friday, same time. Okay. If you are unable to make it, hopefully the recording will work and we won't lose it. Anyway, back to the comment on the learning rate. Learning rate typically is, less than 1, typically 0.01 or so. But it has a huge impact on the learning capability or the result. So there are optimizers that gradually reduce the learning rate. For example, there's one called Adam. So what are those? We'll go into hopefully Friday on that topic, so you'll get a better idea. But for right now, I forgot the code I had given you. We set it to what, 0.1 or 0.1? 0.01, yeah, so it's basically a constant, but typically we gradually change as the system is learning. Okay, so anyway, so how is this different from capability point of view compared to the single neuron network that we created, right? Is it also doing classification?
Yes.
Right? Because again, let's pretend we have two-dimensional data, x, y. So we're feeding in 2, and the expected output will be still class X or class 0, right? Okay, if the data is linearly separable, or first let's take the case it's non-linearly separable. On Friday, I'll actually show you the code where I will visualize it and show you. So let's say this is the decision boundary, right? If we use a single neural network, and let's say we trained it to the best of our capability, will it be able to classify it like this?
No.
No, because single neuron system is a linear classifier. So all it will try to do is basically draw a straight line. Some of the points it may, so for example, this 0 over here, it will classify as an X as an example, right? So this is where more than one neuron is needed. So the terminology goes like this for neural networks. This is called the input layer. Okay, then whatever column we create will, in this example, 2 neurons over here. So this is called the hidden layer. Okay, then whatever neurons we put in the output is called the output layer. If we want to create a nonlinear decision boundary, we have to have some hidden layer neurons. Okay? So the question is how many? 2 over here, 4 over here, 5 over here. Once I show you the visualization, you'll be able to see it a lot better. But if our decision boundary is more complicated, something like this, okay, you will notice the 2 hidden neurons will not be able to do a good job on all the data. It will do a decent job on most of the data, but some data will be misclassified. Okay, so in that case, we'll increase the number of hidden layer neurons. Maybe we'll put 5 neurons over there. Okay, the inputs and outputs are decided by the data. Okay, so we don't have control over the inputs. For example, if it's a 2-dimensional data, there will always be 2 inputs. The same 2 inputs will go to all neurons. Okay, these all 5 inputs will go, so that's the dense connection that I was talking about. Okay, if this is a binary classification problem, meaning class X or class O, like 2-class problem, then typically you will use 1 neuron in the output layer. Okay, if it is, let's say, a classification problem involving 10 classes, for example, you were asked to create a neural network which can recognize digits 0 through 9, right? And let's pretend each one of these is 20 pixels wide, 20 pixels high. So in that case, the neural network that we will create will have how many inputs?
400.
So we'll have 400 inputs. Okay, the neural networks that we are learning right now are simple regular neural networks or dense networks. Okay, dense networks are linear, meaning not linear in terms of the classification, meaning in terms of the data that we feed in. We feed in a 1-dimensional data, even though it's a 2-dimensional picture. Okay, so how will we feed this 20 by 20 pixel data to our neural network? We'll go to the first pixel, and that will become the first value. We'll go to the second pixel, that will become, right? So once we've gone through first 20, the top row, then once we go to the second row, this will be the first pixel of the second row. So basically row by row, or you can do column by column, it doesn't matter. So that's how this will become 400 inputs. So we linearize the 2D into a 1D array before we feed it to the network, right? So then the number of neurons that we will pick in the hidden layer depends on the nonlinearity of the problem. If it is a linearly separable data, how many neurons will you pick?
1.
1. Or simply 10 neurons, you'll basically skip the hidden layer. But if the data is non-linearly separable, which happens to be majority of the time, only very simple problems are linearly separable. So then in that case, we'll pick some hidden neurons. So how many hidden neurons do we pick? Whether we pick 5, 10, 500, 5,000, it depends on the problem. Okay. And gradually through experience also you'll figure it out. Oh, for this type of data, if I use 10 neurons, it does a great job. If I use 20 neurons, it doesn't do as good of a job, right? The number, so let's pretend we picked 50 neurons for the digit classification. So 400 inputs, 50 neurons. Now what about the output layer? Output layer, like I said, is dictated by the number of classes. If we have 10 digits, 10 classes, there will always be 10 neurons. Okay, there's another way to do it also, but this, what I'm showing you, works the best. Okay, Anyway, and these are dense connections. Okay, so for example, if we had 50 neurons, all 50 will feed into the first neuron. All 50 will feed into the second neuron and so on. So can you guess how many weights will there be involved over here?
Number of inputs by the
50 to 10.
So 50 times 10, 500 weights involved over here, right? So all these 400 inputs will go to the first neuron. All these 400 inputs will go to the second neuron and the last neuron. So how many weights will be involved over here?
400 times
20,000.
400 times 50,
50.
right? And then how many biases will there be?
50.
50. How many biases on the output?
10.
So those are the number of model parameters that our network has to learn through training before it's ready, so before it can start to distinguish what digit is it, okay? So anyway, if we use too many neurons in the hidden layer, then there's a concept called overfitting. We're making the model unnecessarily too complex. So what that is, we'll go into more detail. But today, like I said, I wanted to clarify very in clear terms, given any complex network structure, how do we come up with the gradients? How do we train the network? Okay, so
we have 20,000 or so parameters here. So how do you calculate the gradient?
So obviously you won't do it, like we were doing 9 one at a time, right? So this is where we'll go to the matrix form. We'll treat it all as matrices. So I'll, pretty soon after we've learned the straightforward technique, then I'll convert it to matrices and then you'll see how that will be done.
Professor, for classification, we need just one hidden layer according to universal social.
According to the universal approximation theorem, if let's say you put 5 neurons and it's only giving you 90% accuracy, you put in 10 neurons in the hidden layer, it gives you 92% accuracy, right? On unknown data, not on the training data. Okay, so that means initially with the 5 neuron model, your model was not strong enough or complex enough. So, so you could use 2 layers of 5, 5, 5 as an example, then 10 over here for the output. Or instead of using 2 layers, you can put, like I said, 100 or 50 or 80 neurons in 1 layer. So the universal approximation theorem basically said, you really do not have to go to multiple layers. A single hidden layer is enough. It can classify, it can create any complex nonlinear boundary, no matter how complex that is. Maybe it looks like this, sorry, not crosses, but, if you use enough neurons in the hidden layer, it will be able to approximate that boundary pretty nicely. Okay, so now with the 2 hidden layers, 1 output neuron, everybody was able to see how to compute the gradients. Now let's make it more interesting. So now let me go to 2 hidden layers.